Most people walk past it without a second glance. A bright metallic shimmer in the dirt. Sharp crystal faces catching the light. To the untrained eye, it looks like gold. To experienced prospectors, it is dismissed with a single phrase that has discouraged generations. Fool's gold. But what if that name has caused more misdiscoveries than any other mistake in modern prospecting? Pyrite is not the enemy of gold. In many of the richest gold districts in the United States, pyrite is the first signal that something far more valuable lies nearby. The problem is not pyrite itself. The problem is misunderstanding what it is trying to tell you. Gold does not announce itself loudly. It rarely appears where people expect it. Instead, it leaves geological signatures, chemical associations, and structural clues that only become obvious when you stop treating pyrite as a disappointment and start reading it as the geological difference between pyrite and real gold systems data. In advanced mineral exploration, pyrite is not ignored. It is mapped, analyzed, measured, and tracked. In some cases, entire multi-million-dollar gold discoveries begin with nothing more than scattered iron sulfide crystals in otherwise unremarkable rock. To understand why, you have to step far back from the pan, the river, and the surface shine and look instead at the conditions that create gold deposits in the first place. Gold forms deep within the earth, transported by hot chemically charged fluids moving through fractures in the crust. These fluids do not carry gold alone. They move with sulfur, iron, arsenic, quartz, and other elements that react to changes in pressure, temperature, and chemistry. When conditions shift, minerals drop out of solution in a predictable order. Pyrite often forms first. Gold frequently follows. This is why pyrite appears in nearly every major gold-producing region of the United States. From Nevada's Carlin Trend to California's Mother Lode, from Alaska's lode systems to Colorado's mineral belts, pyrite is not a coincidence. It is why pyrite often appears near valuable gold deposits, a byproduct of the same hydrothermal systems that transport gold. But not all pyrite is equal, and this is where most prospectors fail. The shape, texture, location, and alteration of pyrite matter more than its shine. Cubic crystals growing freely in sediment may mean nothing. Fine-grained pyrite locked inside quartz veins tells a very different story. Disseminated pyrite spread through altered host rock signals, yet another geological environment entirely. In high-value exploration, pyrite is classified, not dismissed. The first distinction professionals make is whether pyrite formed in a high-temperature or low-temperature system. High-temperature pyrite tends to be coarse, well-formed, and often associated with intrusive rocks. These environments can host gold, but not always in economic concentrations. Low-temperature hydrothermal systems, on the other hand, often produce fine microscopic pyrite that forms alongside invisible gold particles. This type of gold does not glitter, it hides. In Nevada, some of the most profitable gold mines in history produced gold that could not be seen with the naked eye. The only surface clue was altered rock dusted with pyrite quartz, sulfides, and the first silent gold signal and stained by iron oxides where weathering had begun to break it down. This brings us to the first step in decoding pyrite as a gold signal. Understanding oxidation. When pyrite is exposed to oxygen and water over long periods of time, it breaks down. The sulfur escapes and iron is left behind, staining the surrounding rock red, orange, or yellow. These oxidation zones are not random discolorations. They mark pathways where mineralized fluids once moved and where gold may have concentrated at depth. Experienced geologists pay close attention to these iron-stained zones, especially when they align with fault systems, shear zones, or contacts between different rock types. Gold prefers structure. Pyrite often marks it. The second step is texture. Pyrite that appears as isolated crystals in loose gravel is rarely significant. Pyrite that is finely disseminated through quartz schist or altered volcanic rock is far more important. This texture suggests long-lasting fluid flow rather than a single mineralizing event. Gold needs time and repetition to accumulate. In advanced exploration, even the grain size of pyrite matters. Fine-grained pyrite has a greater surface area and is more likely to trap microscopic gold particles within its crystal lattice. In crystal shape, fractures, and pressure, history explained many modern gold operations. Gold is recovered not because it is visible but because it is chemically locked inside pyrite itself. This is why pyrite is sometimes processed, not discarded. The third step involves location within the landscape. Pyrite found high on ridges, near exposed bedrock, and structural intersections often indicates proximity to the source of mineralization. Pyrite found far downstream, rounded and water-worn, may still be useful, but it tells a different story. It suggests erosion from a mineralized zone upstream, narrowing the search area rather than ending it. In professional surveys, pyrite is used as a pathfinder mineral. Its presence helps geologists trace fluid pathways back toward the original gold source. This is the same logic used in oil exploration, groundwater modeling, and geothermal studies. Gold exploration follows physics, not luck. Another critical factor is association. Pyrite rarely acts alone in gold-bearing systems. It commonly appears with quartz veins, altered host rock, arsenic, chalcopyrite, or carbonatous material. When pyrite occurs alongside quartz veins that cut across existing rock layers, the probability of gold increases. Oxidation zones that professionals pay attention to dramatically. Gold favors cross-cutting structures. These fractures act as highways for mineralizing fluids. Pyrite is often the roadside sign telling you the traffic once passed through. This is where many amateur prospectors make a costly mistake. They see pyrite and move on, assuming the area has already been fooled. Professionals see pyrite and slow down. They measure strike and dip. They examine wall rock alteration. They follow the structure laterally and vertically. They sample systematically rather than emotionally. In the United States, regulatory filings from gold exploration companies repeatedly show the same pattern. Initial surveys identify pyrite anomalies first, followed by detailed geochemical testing and finally gold confirmation at depth. This process is not guesswork. It is repeatable. The final misconception that needs to be dismantled is the idea that visible gold is the goal. In modern high-value gold exploration, visible gold is rare and often economically insignificant. The real value lies in consistency, scale, and geological predictability. Pyrite offers all three. When decoded correctly, it does not fool anyone. It informs. And in the next part, the focus shifts from recognition structural controls that decide where gold accumulates to decision-making. How professionals determine when pyrite is worth following and when it should be ignored entirely. How chemical testing, structural alignment, and regional geology separate real opportunities from endless wasted effort. And how some of the largest gold discoveries in American history began with nothing more than iron sulfide crystals most people walk past. Once pyrite has been identified as potentially meaningful, the real work begins. This is the stage where professionals separate promising ground from geological noise. The difference is not experience alone. It is method. The first professional filter is chemical behavior. Pyrite associated with gold rarely exists in isolation. It alters the surrounding rock in subtle but measurable ways. Silica increases. Carbon content shifts. Trace elements like arsenic, antimony, and mercury begin to appear in patterns that mirror gold deposition. These elements are not contaminants. They are fingerprints of the same hydrothermal fluids that carry gold through the crust. In advanced exploration, pyrite becomes valuable not because it sparkles, but because it reacts. When broken, crushed, or weathered, gold-bearing pyrite often releases faint sulfur odors, produces iron oxides rapidly, or shows microfracturing under magnification. Why surface signs can predict subsurface gold? These reactions signal instability, an environment where gold had the opportunity to precipitate and become trapped. The next step is structural confirmation. Gold does not spread evenly through rock. It concentrates where stress was highest. Fault intersections, fold hinges, shear zones, and lithological contacts are the preferred traps. Pyrite that aligns with these features is not random mineralization. It is directional information. Professional geologists map pyrite occurrences the way investors map market trends. One isolated signal means nothing. Multiple aligned signals form a corridor. Corridors form targets. In the United States, some of the most profitable gold systems were identified not by gold itself, but by long continuous pipe-bearing structures that cut through favorable host rock. When these structures repeat across miles, the probability of economic gold increases exponentially. This is where surface observations meet subsurface logic. Pyrite found in oxidized zones near the surface often indicates that deeper unoxidized sulfide zones remain intact below. These deeper zones are where gold is best preserved. In many cases, surface iron staining is merely the weathered shadow of a much common prospecting mistakes that kill real discoveries' richer system beneath. Modern mining operations routinely invest millions based on this principle alone. Another critical indicator is pyrite deformation. Pyrite crystals that appear crushed, stretched, or smeared suggest that mineralization occurred during active tectonic movement. This is extremely important. Gold is most efficiently deposited when fluids move through rock that is actively breaking and resealing under pressure. Static rock rarely hosts significant gold. Deformed pyrite is evidence of movement. Movement is opportunity. Professionals also pay attention to what pyrite is not associated with. Pyrite formed in sedimentary environments without structural control, alteration, halos, or silica enrichment is usually barren. Shiny crystals and soft rock unconnected to veins or fractures are often misleading. This is the pyrite that earned the name fool's gold. Real pyrite indicators demand context. Context is everything. This is why advanced gold exploration relies on layering information. Geological maps, satellite imagery, geochemical sampling, and physical observation are combined into a single narrative. Pyrite becomes one chapter, not the entire story. When how geologists confirm a gold-bearing environment, pyrite aligns with favorable host rock, strong structure, chemical alteration, and regional mineral trends, it stops being a nuisance and starts becoming a guide. Some of the most valuable gold discoveries in North America were made decades after initial prospecting because early explorers dismissed pyrite-rich ground. They were searching for shine, not systems. Today's high RPM gold knowledge is built on systems. For serious prospectors, investors, and geological thinkers, pyrite is not a failure. It is a question. And the right questions asked in the right place lead to answers that change outcomes. Gold does not reward impatience. It rewards interpretation. The ground speaks in minerals. Pyrite is one of its loudest voices, but only if you know how to listen. Gold is rarely found by chance. It is found by those who understand what the land reveals before the metal ever appears. When you stop chasing glitter and start reading geology, every outcrop becomes information and every signal brings you closer to the truth hidden beneath your feet.